Hi everyone. We'll start today's session. I guess everyone can hear me. Just a second. Let me do full screen. Okay. Welcome to the problem solving session week number 4 of this course titled as Semiconductor Devices and Circuits. And My name is Shomnath Bhattacharjee. I am currently pursuing my PhD in the Department of Electrical Engineering at IIT Jodhpur, and my research interest lies around the fields of TFTs, that is the thin film transistors, that is flexible organic transistors for neuromorphic computing. And previously, I've done my bachelor's in physics and also my master's in electronics. So our weekly class schedule is like on every Sunday from 7 to 9. So as per the schedule, we'll move towards our week number 4, that is titled as recombination generation, charge transport and continuity equation. First we'll recap the last 3 weeks. That is, we have started from the quantum well 3D boxes, 2D boxes and those things, and solved the Schrodinger equation. After that, we have moved towards the solid state physics part of these things and how to implement these Schrodinger equation into solving different cases and everything. And the last week we have studied the density of states, that number of states electron can occupy per unit volume and per unit time and those things. And then after that we have studied the Fermi function, that is what is the Fermi level in a semiconductor, different types of semiconductor, different types of solids. We have already studied in the in the week 2, and then we have doped the semiconductor, and based on that how the Fermi function changes. So there was an intrinsic Fermi level, and there was another one as called as the extrinsic Fermi level. So today we'll learn about several other phenomena that will change, or maybe we can say that it will modify the these Fermi levels and doping concentration, how these density of states will change based on this other phenomena. So today we'll learn about the recombination and generation. So first, the RG mechanism. What is recombination? What is generation mechanism, and how different types of these things can affect the what do I say, like the carrier concentration in the semiconductor, and the charge transport mechanisms as well. So based on the charge transport, we have two different mechanisms, that is the drift mechanism and the diffusion mechanism. And based on that, how every parameter changes. And finally we'll conclude the session with the continuity equation. Like this week, what I am going to do is that I'll briefly describe this phenomena, and then we'll move towards the problem sides. From the next week, we'll move towards the main topics, that is the metal semiconductor junctions, that is the junctions, that is PN junctions, PIN junctions, and those things. After that, we'll move towards the transistor, that is the main aim of our course. So this is the last week, that is that will they describe the basic things of this course. So first, we'll move on to the basics of RG mechanism, that is the just a second. Recombination and generation. So first we need to know what is recombination and what is generation. So the basic thing in this case is that something recombines and makes something like a newly different entity. So let's say first, no, I guess first we need to describe what is generation. So let's say we have a photon, that is a charged particle. So let's consider we have an excited photon, and based on some circumstances this excited photon splits into two equal parts. So there may be a electron, we can write it as like this, E minus. So there may be a it divides into two equal parts. So one part is called the electron, another one is a hole, that is H plus. So what happens that a certain photon which is already excited, it is like it increases its energy of the total semiconductor, and it gets divided into two different parts, that is the electron and the hole. So this kind of a process also increases the total energy. This is called an phenomena of generation. So similarly, a case where we have this kind of electron and a hole, and they both recombine, so they gets mixed. So what happens, they results in a particle called photon. So this, in this case, what it happens that it reduces energy, and this phenomena is called recombination. Sorry, whereas this one was generation. So there are several types of recombination and generation phenomena, and based on that, we can have several examples, and then we'll talk about those. The first one is B2B recombination, that is the band to band recombination. What happens in this kind of a thing is that, let's draw this like this. So this is our conduction band and this is our valence band. Uh, just a second. So this is our conduction and valence band. So let's say we have some particles. These are our electrons, and we also have, let's take this color, and we have some holes. Oh, I guess this is not visible. And we have several electrons and several holes. Similarly, we'll have these electrons in the conduction band. So what happens in a B2B, that is band to band recombination, electron loses its energy and it comes down to the valence band and recombines with this hole. Based on that, just a second, electron loses its energy and it recombines with this hole. So this kind of a recombination is called band to band recombination. Similarly, there can be a similar kind of a case where we'll have this kind of a structure similar, and we'll have some holes like this. Sorry, electrons like this, and few holes as this. Now, what happens that a certain electron gets excited and moves to the conduction band. It moves here, and based on that, here a new hole is created. So this is a phenomena which is called the B2B. Let me write it down. So this is known as band to band generation. So in band to band generation and band to band recombination, what happens that there's a direct exchange of electron or holes between these two bands, that is the conduction band and the valence band. So there's a direct exchange between band to band, that is why it's called B2B recombination and B2B generation. So these are one of the most basic things, but what happens afterwards is, so the third phenomena is known as the recombination generation, center based recombination. So this is one of the most important recombination generation phenomena, where what happens in this case is that we have our conduction band here, we have our valence band here, and the basic things happen here as well. So we'll have few electrons here. There are, let's say, few holes here as well, and based on these holes there are few electrons in the conduction band. Now what happens in this case is that there's a new band which is known as the ladder state or the trap state. So here I am showing just a single state, but there can be multiple states as well. And based on these states, so what happens here is that a single electron can move to this state, whereas it doesn't require that much energy when like let's say in this case of like generation case, a B2B generation, in the second case, what happens that it needs a some amount of energy that is greater than equals to the Eg, that is the band gap, and it can then move towards the conduction band. But in this case what happens that it requires much lesser energy than the Eg. So what happens here is that it creates a hole in its place and it moves towards here, right? And based on this, so and further if it gets much energy, so it can move towards the conduction band as well. But let's say it happens like this. So the basic phenomena here is that it becomes much easier for an electron to jump to the trap state or the ladder state, whereas an hole to come to the valence band from the trap state. And like this exchange is much easier than the band to band. Band to band recombination and band to band generation. Similarly, similar phenomena can be shown here as well. So this is called as the RG center based generation. So this is also the same phenomena, whereas we have the conduction band, valence band, and we'll have another trap state or the ladder state. And based on that, let's say we have this kind of a structure. So it's must like it is much easier for an electron to jump to this trap state and also an hole to jump to this trap state as well, so they can recombine very easily. So it requires much less energy than the previous B2B recombination and B2B generations as well. So apart from that, so these two are the basic phenomena, whereas the second one is much common than the first one, obviously. And apart from that, there are several other phenomena as well. So one is exciton assisted recombination. I'm writing both at the same time, and generation. So what happens in this case is there are excited these are kind of a excited particles which is able to move even like before the recombination and after the recombination. So if there is a structure like this, this is CV. So out of these particles, some may be able to move inside the semiconductor as well. So these have the mobility to move inside the semiconductor, and these kind of a electron or these kind of a hole can create like a several assisted recombination and generation cases, and these kind of a phenomena is called the excited assisted, and most of these cases often happens in organic semiconductors. Be- just a second, sorry. organic semiconductors. So as a matter of fact, like just it's going a bit towards the opposite direction, but let me explain it a bit. So in a conventional semiconductor, there is a conduction band and a valence band, but in an organic semiconductor, there is no proper band. So what happens, like we assume that based on the pi bonding and the anti-pi bondings, there is something called a valence band and a conduction band. So what happens here is that this band is not exactly a linear one, so it can be like this or something like different. So what happens in an organic semiconductor is that there are several particles here or here. So this is, in this case it is called, just a second. So it can be like this or it can be like different structure, it can like have different structures and those things as well. So we can have it here, we can have it here, and these kind of a structure. So this is called the, so based on the molecular orbital theory of the organic semiconductors, we have two of those things, that is the HOMO and LUMO. So the full form of HOMO is highest occupied molecular orbital. So it has a very clear similarity with the valence band. So a valence band is that the highest possible state electron can have with like in an equilibrium state. So it is very clearly a similar, it has a similarity with the valence band, whereas LUMO is the lowest unoccupied molecular orbital. So the last unoccupied molecular orbital, or this is very clearly has a similarity with the conduction band. So based on this phenomena, so there can be several these kind of atoms which can freely move inside this semiconductor. So this kind of phenomena, that is the excited assisted one, happens mostly in the organic semiconductors. Then we'll move towards another one of the most important RG phenomena, that is the impact ionization. So what is an impact ionization? So based on an impact from an external particle, it can be an electron, it can be a phonon, it can be a photon, these kind of a things. But based on this impact, what happens that that is based on an impact. So it is based on an impact through a collision. It can be a collision with a excited particle. It can be a collision through another electron. So electron hits another electron, and based on that, one electron gets excited and goes to the conduction band, whereas electron stays and or comes down to the valence band. So it can like let's say an electron can replace another electron space, and based on this, if there is a recombination or generation phenomena, it's called as the impact ionization. So it's based on the impact or based on a collision effect. So so these are the basic like phenomena of recombination and generation. So what happens in these cases are that we have a set value of n, that is the carrier concentration for like n, that is the electrons, and also p. So So we have a fixed value of n and p. Now, if a photon, let's say a photon is breaking like this, so it's generating an electron and a hole. So based on that, what will happen that number of electrons will electron concentration will increase, and also number of hole concentration will also increase, right? So this is the basic phenomena why we need to study the effect of recombination and generation inside a semiconductor, is that the carrier concentration changes with respect to these interactions with photons, phonons, and these kind of a things. So after that, we what we have learned this week was no, let's use the next page. After this, what we have learned this week is that the concept of direct and indirect semiconductors. So in a EK plot or EK diagram, so energy momentum diagram, in an energy momentum diagram, what happens if we have a, sorry, and I use this one, this one. So in a energy momentum diagram, if the conduction band and the valence band, so the lowest point of the conduction band and the highest point of the valence band, both are in the same value of, let me write it down. So if they are in the same value of k, that is the momentum value are same, we can say that it's a direct band gap semiconductor. And if it's shifted towards right or something, so it's called, like if the k value doesn't match, it is called an indirect semiconductor. So let me write it down. If k is same for lowest point of conduction band and highest point of valence band. So in this case, this is called as an direct band gap semiconductor. And if this is not the case, let's say, maybe I'll first draw this. So in this case, this is K and this is E. So this is the lowest point of conduction band and this is the highest point of valence band. So there's a clear difference between the K value of the lowest point of conduction band and the highest point of valence band. So this is called an indirect band gap semiconductor, or in short, that is the indirect semiconductor. So let's remove it, I guess. So based on this, we can assert that if there is a photon interaction or a photon plus phonon interaction. The next topic we have learned this week was, I'm not going into depth of this because like it was derived very clearly in the course. So the next topic was capture cross section, and after that we have learned about the quasi Fermi level. This is a very important phenomena. So we'll go towards a bit of details of these. So what is a quasi Fermi level? So up until now we have learned that in a intrinsic semiconductor we have a Fermi level, right? So these Fermi level was termed as, at first we have termed it as the Fermi level, the basic Fermi level. After that, what we have we have assigned the name that is the intrinsic Fermi level. Fermi level. So if we draw it out, so it would look like this. So if this is the semiconductor, this is the conduction band, and this is the valence band. Now the intrinsic Fermi level would be here, E f of I. So let's rewrite it. as EC and EV. Okay, so EF of I, EF of I was termed as the intrinsic Fermi level. If the semiconductor is doped, then the Fermi level shifts. So the shift is based on if it is a N-type doped or P-type doped, but the Fermi level shifts, and this is called as the extrinsic Fermi level or just the Fermi level. So based on this, we can say that, let's change the level like this. So based on this, we can say that this is the new Fermi level or EF. Okay. So this is the extrinsic Fermi level or the basic Fermi level, or we can say it the Fermi level. Now, what happens in this case is that, so it was until we have kept the concept of like recombination and generation or these kind of a things. So after considering recombination and generation, so after considering this phenomena of recombination and generation, what happens is that value of carrier concentration changes. So there's a change in the value of carrier concentration, and based on this change in the carrier concentration, what happens is that based on the carrier concentration calculated, based on the Fermi level calculated from both of the carrier different carriers, what happens that we get two different values of EF. That is, the Fermi level has two different values based on if we are calculating it from the whole or if we are calculating it from the side of, like, let's say electron. So what happens, we get two different Fermi levels. So we can say it as quasi Fermi levels. So up until now we had a single intrinsic Fermi level and single intrinsic Fermi level, but based on this phenomena of recombination generation, we would have two different Fermi levels. So these are EFN and EFH or P, you can say. So there are two different Fermi levels when we are considering the fact that there is recombination and generation going on. So it's stated as the quasi Fermi level. So let's have an example. So based on this, what happens? So based on this, what happens is that let's say in a semiconductor there is like 10 to the power 17 number of electrons and 10 to the power 3 number of holes. So these were the number of holes and number of electrons in that. Now let's say in that uh, we have included 10 to the power 10 number of electron and hole, new electron holes based on generation. So based on electron and hole generation, there are new 10 to the power 10 number of electron and holes. So based on this, we can say that now the new number of electrons are 10 to the power 17, the old ones, and the new ones, that is the 10 to the power 10 number of electrons. So it's clearly 10 to the power 17, as 10 to the power 17 is much higher than the number of 10 to the power 10. Whereas the new number of holes, new so the new number of holes are 10 to the power 3, the old one, and 10 to the power 10, the new one. Now, what happens in this case? It becomes 10 to the power 10, as 10 to the power 10 is much greater than 10 to the power 3. So, the previous number of so we can say that electron old is the same number that is the electron new, but number of holes old is much less than the number of holes new. So based on this factor, if we are calculating the value of EF minus EI, so this is how we calculated the value of Fermi level. So based on this, we can write it as ln n by ni. So as the number of n has increased, from this we can calculate the value of EF, and based on this we can also calculate the value of EF. So this would have minus kT ln of P by Ni. So based on this, we can calculate the value of EF, and we can check in this case that the value of EF in both the cases will be different, and it would have a distinct value. And based on that, we can say that this old EF will remain the exact same for the electrons. So we can maybe redraw it that this EF has sorry. So this EF will become to EF of n, because there is no certain change in the number of electrons in the material, but there's a there's a new higher number of holes in the material, and based on that we'll have another value that is called as the, so this will give us the value of EFP, whereas this will give us the value of EFN. So these two both are called at the same time called as the quasi-Fermi level. So this is the this one is the quasi-Fermi level for the electrons, whereas this one is the quasi-Fermi level for the holes. And so after that, what we have learned is what is the resistivity of the material through using Ohm's law. So how have we calculated that? We have calculated that through the drift phenomena. So we have already got J drift was found out to be this. Let's not write it like this. So we have got the value of J drift here. And after that, from Ohm's law, what we can get is that, let's write it down like this. So from Ohm's law, what we have got is that the value of I should be J into A. So from this, we can write it as like this. Q, that is the total charge. So n mu n for the n type and p mu p for the p type, and the applied electrical field. Based on that, we can write it like this. So this is nothing but the change in the applied voltage. So from this, if we are integrating both the sides, so we'll have this difference 0 to V Q n mu n p mu p dV. Okay. So based on this, we know that this term is completely constant with the change of x. So we can write it as uh, integration 0 to v dv 1 divided by q n, sorry, q n mu n plus p mu p multiplied with the value of I. Now, so based on the drawing and everything, you can see in the videos. So we have considered it as VA by L, and this value would fetch the value of n mu n plus p mu p multiplied by I. So this is exactly like the Ohm's law. And we can say resistivity is nothing but 1 by q multiplied by n mu n plus p mu p. So this is how we calculate the value of resistivity. And based on the diffusion phenomena, we have got the value of J, that is the J diff equals to Q dN. So this is diffusion coefficient dx minus of Q dp, as the holes oppose the flow of this electrons, and based on that this comes out to be this. Okay, so this was based on the diffusion phenomena, and this was based on the drift phenomena, that is q mu n q n mu n plus p mu p. And if we are combining both the effects, so based on this, total current for electrons would be, that is Jn. So this would be J diffusion for N and J drift for N. And we'll just combine both the effects separately. So J diffusion is Q dN dN by dx, and the drift one was Q n mu n, this. And similarly, Jp, that is the total current for holes, would be J diff of P plus J drift of P, and we can write it down as minus Q dP dP dx plus QP mu P, this. So this is the total current for electron. This is the total current for let me write it down. Total current for holes. Now the last topic we have learned this week is the continuity equation. So I'm not going into the details of how to derive this and that. You can check that out. I guess it was the second last or the last video of this week's. I'm just gonna write it down. So what is the importance of continuity equation? First, we need to learn that, and then we'll learn what is the continuity equation and what do we get from solving it and those things. So the main thing to like know about the continuity equation is that first, to understanding the device, that is the working principle, how the device is working and everything. And the main thing that is to, like, if we are going to simulate a transistor or a diode, we need to obviously know the continuity equation of that thing anyways. So is that simulating diodes and transistors, to simulate a device correctly, like a diode or a transistor, we need the continuity equation. So just let me write it down. So for the electrons, the continuity equation is dn dt a dx jnx minus jn, slightly at the slight disposed position, and then divided by minus q to a plus, just a second, sorry, gn minus rn. What's happening? I don't know. Just a second. Gn minus rn, generation and recombination rates, a dx. Similarly for poles, values are dp dt a dx equals to jp of x minus jp of a slight displaced position, divided by Q, as the charge is positive, A plus Gp minus Rp multiplied by A dx. So these are known as the continuity equations. And the basic thing to learn about this is that to completely understand the working principle of a semiconductor and of a material, to know the device much better, and also simulating diodes and transistors. The ultimate goal is to clearly simulate a diode or a transistor or a certain device. So this is the basic outline of this week's videos and the lectures. And I'm not going in detailed process how to derive the continuity equation and how to derive the capture cross sections and those things, because that's completely in the video. I have just touched on all the topics like that has been touched by professor. And now we'll move towards the problems that we are going to solve today. So I am writing down the problem. So from this week, what we are going to do is that we'll give let's say 2 to 3 minutes for the basic understanding of the questions, and after that, after 2 to 3 minutes, I'll give some hints to solve that question, and after that, I'll give the solution if no one is able to get the total solution and those things. Okay. The first one is, let's start with maybe a basic question or something. What is the location of the traps inside the band gap that produces the most efficient trap assisted recombination? So I'm giving several options. That is also after solving this question, you have to also explain why you are choosing that, and what's the problem with the other cases as well. So this would be very close to the conduction band, very close to the valence band, near the middle of the band gap, and also it is dependent of the position of the traps inside the band gap. And also to add this, there are a few assumptions as well. So minority carrier lifetimes of holes and electrons are equal. So which will be the correct one, and why is it? I'll give 2 minutes to think about it, and you can answer me back. So which one is correct? Anyone have any answer? I'm sorry. Oh, I guess this one has been disconnected. I don't know why. Hmm. So which one is correct?
Hello, sir.
Yeah.
Near the middle of the band gap.
Okay. So you are saying this one is correct, right?
Yes, sir.
And why not the first and the second one? Like if you can explain that why it is the middle of the band gap that like you are thinking that that's the right answer, and why not the close to the conduction band or close to the valence band?
It's because minority carrier lifetimes, that is tau,
Hmm.
for holes and electrons are equal. So the recombination rates and generation rates are equal.
Yes. So no, no, no. Let's say if just a second. Oh, okay, that's fine. So let's say traps are closer to conduction band. Okay. So why will it why will it not be the most efficient one? Can you just break down the things for the others? Think of it like if it's near to the conduction band, which kind of a carrier will it attract?
Electrons,
Yeah. So the electrons will be attracted more, and holes will be attracted less, right? So that's why it is more inefficient, because if let's say just a rough number, let's say 10 electrons are there and only 3 holes are there, so it would be obviously inefficient, right? Because there are not that there are like there are no case that 7 other electrons will be recombined with the other holes as well, so it's very inefficient. Similarly, let's say if the traps are closer to valence band, the opposite will be there. So let's say there are 10 number of holes and only 3 number of electrons, so it would be inefficient as well. But if it's at the midpoint, the main thing would be that there would be much lesser electrons and much lesser holes. Let's say only 7 holes and 7 electrons, but they will recombine fully because the carrier lifetimes are equal. So based on that, there will be a full recombination. And if we are considering the number of recombinations in these cases, the most efficient one would be at the midpoint. Sorry, it would be the most efficient one. Yeah, that was the correct answer, anyways. So we are moving to a more numerical one. So let me write it down first. A semiconductor has a cross-sectional area of 1 centimeter cube, okay, and a thickness of zero point 0.1 centimeter. Now determine the number of electron hole pairs that are generated per unit volume per unit time, okay, by the uniform absorption of 1 watt of light, that is a photon, at a wavelength of 6300 Amsterdam. And in this case, also assume that a single photon generates a single electron hole pair. So I'll go through it again, that a semiconductor has a cross-sectional area of 1 cc and it has a thickness of zero point 0.1 centimeter. Just zero point 0.1 centimeter. We have to determine the number of electron hole pairs that are generated per unit volume and per unit time. And the photon that was absorbed was 1 watt of light, and the wavelength was 6300 Armstrong. And we know that a single photon will generate a single electron in a single hole. If someone of you can explain how to solve this. I just take 2-3 minutes and try to solve this, and then we'll discuss how to solve this and what is the exact solution as well. Also, if anyone is able to solve the question, write it in the chat box, or you can turn on your mic and like give me the answers as well. So I'll give you some hints. So first we know that the power of the source that was absorbed was 1 watt, and the source lambda was 6300 Armstrong. Okay, and the semiconductor volume is given as 1 cc, 1 centimeter cube, and semi semiconductor thickness is 0.1 centimeter. Okay, so these are the given values. First, we need to calculate the value of E, that is nothing but h nu, where h is the Planck's constant, and constant, and we know nu is the frequency, which is nothing but c by lambda, where c is the speed of light and lambda is the wavelength. So from here we can get the value of nu, and we can get the value of E, that is from the value of h and nu, and from that we can get if we get the energy of the this what do I say, like this absorbed light. So we can, from that we can get the number of generated photons, and from that we can get the number of generated electron and hole pairs. So try to do this.
Sir, the value of E is 3.15 into 10 raised to the power minus 19.
How much is it? Just a second. Yeah, how much is it?
E,
3 point,
E
yeah, 3
3.15
into,
10 raised to the power minus 19.
yes, I've also got that. And what was the value of nu?
So nu is C by lambda.
Yeah. So what was the value of it? Like, how much have you got it?
So
C,
4.76
C,
into 10 power 14.
10 to the power 14. Okay. And now then, like from E, we can get the value of number of photons generated per unit volume. No, for unit volume per unit time. So what was the value of it? Number of, first try to get this. Number of generated photons. What is it? How much is it? It is nothing but 1 by E. So 1 by 3.15 into 10 to the power minus 19. Just calculate it. How much is it? Just a second. Let me calculate it.
3.17
3.17 into
into
10 to
10
the
raised
power
to the power 18.
18. Okay. So this is photons per second, right? So now we have to calculate the number of generated photons per unit volume. So number of this would be per unit. Just a second. It was sorry. This is cross-sectional area. Now, so per unit volume, it would be nothing but 3.17 into 10 to the power 18 divided by the volume. So it would be 1 cc into zero point 0.1. I guess there's a mistake here. It should have been like this. There's a mistake in the question, maybe. That's why. So it should be 3.17 into 19 then. 19. So this is in photons per unit volume per unit seconds. Okay. So as we have assumed already that there's a single electron hole pair for the single photon. So number of generated electron hole pairs per unit volume per unit time is nothing but 3.17 into 10 to the power of 19 is the number of that. And this would be in, sorry, this would be in cc, right? So this is eh pairs multiplied by centimeter minus 3 second minus 1. So this is the number of electron hole pairs per unit volume per unit time. So the value is 3.17 into 10 to the power 19 electron hole pairs per cc per second. Sorry. So we'll move. If anyone have any questions on this, or we can move to the next question.
Hello, sir.
Yes.
Sir, how the number of generated photons is equal to 1 by E?
Yeah. So like this is the what is the but like what does E mean here?
Is the energy?
Yes. So the energy of the absorbed light, right?
Yes,
So
photonic
based
energy.
yes, so based on this light, what happens? There is a number of generated photons. So this energy is directly converted from the light to the generated electron and holes. So there will be photon number of photons generated directly. So if let's say if we have a material like this and a light is incident upon this, so the amount of absorbed energy is converted directly to photons inside this material, and inside that material each photon is generating a single electron and a single hole. So it's the direct if yes, obviously we are considering that there are no loss of energy in between. So if there is a like, let's say as there is nothing mentioned, we are assuming that there is no loss of energy in between, but let's say it gets totally absorbed inside the material. The total energy will be directly converted to the number of photons. From maybe you can like understand from this as well, right? Hc by lambda, just try to calculate the units as well. From that you can also get this value.
Okay, sir.
Yeah. Now we'll move to question number 3. So in a semiconductor, there are four scattering mechanisms. If the first one is only present, the value of mu1 is 2000 centimeter square per volt second. If the second one is present, the value of mu2 is 1500 centimeter square per volt second if the third and fourth ones are present. Value of mu34 is 1000 1000 centimeter square per volt second. I guess so the value of this is 1000 centimeter square per volt second. Now the question is, what is the combined value of mu? What is mu total, let's say? So what is the combined value of mu? Hmm. So we need to get the value of combined value of mu. Try to solve this. So let me give you a hint. The basic thing is, if we are saying mu in all of the cases, so it should be mu1 plus mu2 plus 1 by mu3 plus 1 by mu4. Now try to solve this.
So 461.54.
So what is the value?
461.54.
461.54. So let me check it. Anyone have got the same value or a different one? Let me check. So it's 2000 plus 1500 plus divided by divided by this value, right? 461.54, right? So this is the correct answer. So first we know that mu1 we have got is 2000. Sorry, sit like this. Yeah, so mu1 is 2000 centimeter square volt second. We know mu2 which is 1500 centimeter square per volt second, and we have mu34 as 1000 centimeter square volt second. So first we need to know that mu 34, how we have calculated mu 34, right? So 1 by mu 34 will be 1 by mu 3 plus 1 by mu 4. Now, if we are considering 1 by mu all, if we are putting the value, then it would be 1 by 2000 plus 1 by 1500. And by this we can write 1 by mu 3 plus 1 by mu 4, right? This is nothing but 1 by 2000, 1 by 1500, 1 by mu 34, or 1 by 2000 plus 1 by 1500, 1 by 1000. And the value comes out to be 461.5384. We can write it as like this: 461.5 or 54, let's say. So this is the value. Now, if anyone have any question, please ask me. Otherwise, we'll move to the next one. If
Sir,
yes.
sir, how can you write 1 by mu all equal to 1 by mu1 plus 1 by mu2?
Oh, so how can we get this, right? So
Yes, sir.
to explain this, I have to plot this, but I guess how can I explain this? So this is directly from the equations, but like, to explain this, I have to plot this. If you want the total explanation, I can give it to you after maybe the problems or something, or maybe I can attach that as well, because I need to draw the different scattering mechanisms. And when we are talking about the scattering mechanisms, let's write it like this. So it is actually okay. So I'll attach a separate sheet where I'll describe it, and then with this lecture note I'll attach in between. Okay,
Okay,
because
sir.
I don't actually the problem is that I don't actually remember the total derivation right now. So maybe I'll attach that inside that. Okay.
Okay, sir.
Yeah. So Q4. So let's have an.
So,
Yes.
how we have get the value of 461.5384?
Is
Because
there a
when we
calculation?
are when we are dividing these values, it's nearly upon 216.66.
Just a second. Just a second. Let me recalculate it again. So 1 divided by 2000. I'll write it down here. So this one comes out to be 0.0005. This one comes out to be 1 divided by 1500s. So this is 0.00066. And this one is, so this is completely similar, 001. So if we are adding this up, 0.001 plus 0.00066 plus 0.0005. So you are getting the value of this, right? 0.00216.
Yes, sir.
Yeah, so uh, okay, so here what I have done is that I skipped a step. Because of that there's a miscalculation or misconception. So if we are adding this, so we'll get this, but this is the value of, we need the value of mu all, right? So we have to inverse it again. So 1 divided by 0.00216, 0.00216. So the value was, what was the value? 462.96 I am right now getting. But at that time I haven't assumed anything, so I have divided the total values. Let me do that again. So 1 divided by 1500 plus
462.96, sir. Yes.
462.96. Okay. So I have got that anyways. So 1 divided by the history answer it. So yeah, so it was coming out to be 461.538. So this is as, because this is 666 dot dot. So by inversing this value, we are getting this value. Is it okay now?
Yes, sir.
Ah, yes. Because we need to we needed to get this value, the mu all, for all the scattering mechanisms, and in that case I have inversed, but like I haven't written that, so the value will be like this. Are there any other problems? If there is none, so we'll move to the next one. So for a energy band diagram, we have a nx of 10 to the power 15 exponential of qzx divided by kt, and we have the value of z as 0.1 volt per centimeter, and x has a unit of centimeter. If we have kt by q equals to 0.026 volts and value of dn as 36 centimeters per second, then what is the electron current density at the value when x equals to 0? And the plot given is like this. This is E in EV values. This is K. Sorry, this is X. We have this conduction band and we have this valence band. So this is EC. This is EV. The slope is 0.1 EV per centimeter, and this is at x equals to 0. And also we can write it down like this: d by mu equals to kt by q. So try to solve this. What is the electron current density at x equals to 0? So let me write it down. So this is Jn. We have to find out the value of Jn when x equals to 0. Try to solve this. Has anyone got any answers? Or should I give you a hint? Maybe I'll give you a hint. So the value of Jn is the total value of drift plus diffusion, and we can write it down as Qn mu n E Q dn dx. So we have to found out which are the values we know and which ones we don't. Let's start putting the values. Just try to put the values here and you will got to know what I am talking about. So let me write down the values here. So we know that the value of kT by Q is 0.026 volts. We have the value of dN, which is 36 centimeters square per second. X is equals to 0. Z is equals to 0.1 volt per centimeter. We have the value of Nx directly here, so we can put it directly down there and we can differentiate the value as well. So these are the given values here. Maybe then I'll solve this one. So first thing was to solve this. Before that, just get this what we can get from this figure, right? So we got to know that dEc by dx is equals to minus 1 ev per centimeter because the slope is already written like this. So we can say that dEc by dx equals to this, and also from this we can say that E is 1 by q dEc by dx, right? Now from this we can write 1 by 1 into 0.1. So I am writing it as 1 because this is 1 ev, okay? And because the value of dEc by dx is equals to zero point 0.1 ev, so that's why I am using ev here, and based on that the value would be 0.1 volt per centimeter, right? 0.1 volt per centimeter, yes. So this is the value here. Now we can directly put all the values here. So let me rechange it to E because I am writing E here. So we'll move to the next page. So Jn, we have got Qn mu n E plus Q dn dx. First we can get this. Now we have the value of n. So the value of n was 10 to the power 15, 10 to the power 15 e to the power qzx divided by kt, and we have multiplied by mu n, and we have got the value of e as 0 0.1 minus 0 0.1, sorry. So this is minus 0 0.1, okay, plus not q, the value of dn. So the value of dn was 36. So the value of dn was 36, or we can write it down as dn, let's say, and we have to differentiate the value of dn dx. So this was the value of n, right? So from that we can write it down as 10 to the power 15. Oh no, so like from this we can also write it like this. 10 to the power 15 exponential of qzx by kt. Okay, and the other terms will be qzx by kt, qz by kt, right? q days, if there is any like miscalculations or like mistyping, please let me know. Okay, so this one would be 10 to the power 15.
Okay.
Ah, yes.
So
Is there
please
any issue?
repeat. Uh, so please repeat that part. How
Which
we
one?
put the value of dn by dx.
Yeah, so dn by dx is 10 to the power 15, right? So this is this one is the value of n. So we are
But in
just
question, the value of dn is 36, sir.
where? No, no,
Okay.
I haven't put the value of dn right now. So I'm just
Okay.
keeping it because you will get to know eventually. But I'm just not putting the value of dn right now. So this is just the value of nx, and this is the differentiation part of that qz by kt, and x was anyways there, and 10 to the power 15 was a constant number. So we have got this value, right? Sorry. So we
Okay,
have
sir.
got 10 to the power 15 e to the power of, or we can, I guess, we can just keep it outside anyways, e to the power of qzx by kt, or we can write it as minus 0.1 mu n plus dn qz by kt. Now from this equation we can directly write as from the Einstein equation we know dn by mu n equals to kt by q. That's why I was not putting the value there. So q 10 to the power of 15 e to the power of qzx by kt, and if we are putting this value minus of 0.1 mu n, just a second, minus of 0.1 0. I guess I have missed. Okay, minus of 0.1 mu n plus dn is kt by q, so it should be kt by q multiplied by mu n multiplied by qz. Okay, now sorry, so the value of z was how much? The value of z was 0.1. So maybe here we can write it down directly. So 0.1, and this is the value, and this is the Einstein's equation. So we can remove it from here as Einstein's equation. Now we can write it down like q multiplied by 10 to the power 50, or we can write it like n of x, right? Minus 0.1 mu n, and there were some values kt by q, qz by kt, right? So kt is getting cancelled, q is getting cancelled, plus 0.1 into mu n. So this is directly 0. So we don't even have to put the value of x as 0. So we can get the value directly as 0. So because both the terms are cancelling out. So the question was electron current density. So the value of, sorry, electron current density is 0, and at the point x is also 0, right? So both the cases, even if we don't have the value of x as 0, anyways the electron current density is found out to be 0. Are there any questions in this? So like as I was saying that because we have this equation, that the Einstein equation, dn by mu n or dp by mu p is equals to kt by q. Based on that, we were not putting the value of dn directly here. We are just getting the value, like we are just putting the Einstein's equation like here, and that's why we can get the value directly 0. Otherwise we have to calculate all the values, and we have to put x equals to 0 in e to the power 0 and everything. Are there any questions in this? If there are none, then we'll move to the next one.
Hello, sir.
Ah, yes.
Sir, how can you plot the graph?
No, I'm not plotting the graph. It's directly from the question. So this is the part of the question, and they have already given the slope is minus 0.1 EV per centimeter. From that, we are just arising on this conclusion, this one. Sorry. So from that, we are arriving onto this conclusion, right? That d of EC dx equals to minus zero point 0.1, and also for d of EV dx is also minus zero point 0.1, because we can see that these two are parallel lines and they have given the slope. So we are getting the dEC by dx, nothing but that. The graph was already inside this question as well. Is it okay?
So slope is given that minus 0.1 electron volt per centimeter.
Yes.
So how can you write this?
No, no. So like, so this is EC, right? EC is the energy of the conduction band, and there is slope written as, so the x-axis was x, right? So the slope is dE by dx. Is it okay or not?
Yes, sir.
Yeah, so dE by dx is zero point 0.1. So as these are the two things, we are seeing that these two would be anyways parallel, right? So maybe I'll use a different color. Just a second. Yeah, so we know these two are parallel. So we can write it as dEC by dx and also dEV by dx. Both are equal to the slope anyways. So we have got the slope as zero point 0.1, zero point 0.1, zero point 0.1 EV per centimeter. So we can write it as like dEC dx equals to minus 1 EV per centimeter. We're just write, they have written the slope and we are just writing it as dEC by dx. That's it. Is it
So
okay?
how the slope is minus?
No, no, the minus is already given, right? I am not concluding that it is a minus slope or a plus slope or something. They have given in the equation, sorry, in the question, it was given in the figure was already given in the given in the question, and they have given the slope is this. We are just writing it down that the slope is nothing but, from the plot we are just writing it that the slope is nothing but dEC by dx, right?
Okay,
That
sir.
that part is okay, right? The slope is dEC by dx. So I am just writing it down like this. This is my part only. And the other one was already written in the question itself. The slope was written as minus zero point 0.1 EV per centimeter. It was already written there. We are just writing it down as dEC per dx equals to the slope, which was already given as zero point 0.1 minus zero point 0.1 EV per centimeter. We're just putting the values.
Okay, sir.
Okay. Yeah. So we'll move to the next one. That is question number 5, right? Yeah. Question number 5. So an intrinsic.
Sir,
Yes.
so what will happen if we directly substitute the value of x as 0 in the end term?
We don't have to put it there, right? Because then this sorry, just a second. Then this term will bloat up actually, e to the power 0. So we don't have this term. So q into 10 to the power of 15. So that's why I have just converted it to nx anyways. So we have to calculate the value of n0 at that term. And if there is, like, let's say there's a plus or something, the values were different a bit. So this would have been a different values. But anyways, the this term is anyway 0, right? So we are not
Yes, sir.
calculating that. So the electron current density is everywhere 0, not only at the point of x equals to 0. It's everywhere 0. So even if the value of x was like 100, 200, 10 to the power 3 or 10 to the power 4 or something like that, It would have been 0 anyways.
Okay, sir.
Okay. So we have an intrinsic semiconductor which is doped with argon with concentration of 10 to the power 16 atoms. So we have got the value of Nd, and if a small amplitude of low frequency voltage V in is applied across the semiconductor block, there is a I in current flow, assuming the cube shaped semiconductor has side of 10 micrometers. Find dV in by di in. So change in voltage with respect to change in current, and also it's given that all the dopant atoms are are ionized. Sorry. Intrinsic carrier concentration is 10 to the power 10 per cc. Electron mobility is given as 10 to the power 3 centimeter square per volt second, and hole mobility is given as just 350 centimeter square per volt second. So we need to get the value of dV in by di in. So if we are writing it down, so we have got Nd as 10 to the power 16 per cc. We have in we have Ni as 10 to the power of 10 per cc, and we have the whole mobility, that is, this is mu n and this is mu p. This is mu n equals to this is mu p equals to this, and all the dopant atoms are ionized as well. So we need to get the value of, so from this, how can we get the value of del V by del I? What is it? How do we get that? This is resistivity, right? So we need to get the value of resistivity here. Try to solve this. A hint is that my hint will be, first calculate the value of n, then the value of p, and from that you can get the value of del IV, del I in through the application of rho as well. That is the resistivity values. Try it out. maybe I'll give you all a hint. So, from this case, what we know is that the new n, the value of n, would be the old value of n plus nd, right? And from this, we can know that the value of n would be 10 to the power 16 cc, as nd is much greater than n. Okay. So as nd is much greater than n, so 10 to the power 16 plus 10 to the power 10, it is nothing but 10 to the power 16. So we have got the value of n. So from that, we can get the value of p, that is the intrinsic carrier concentration squared divided by the electron concentration. So from this, we can get the value as 10 to the power 20 divided by 10 to the power 16. So this is 10 to the power 4, or we can say nearly 10 to the power 4. So this is nearly 10 to the power 4 per cc, and this is also per cc. So we have got the value of n, we have got the value of p, we have got the value of mu n, value of mu p. So from this, what we can write is that uh, let's write as the semiconductor block has the dynamic resistance. So the dynamic resistance is nothing but dVin by dVi of n, right? So it is nothing but rho L by A. From a cubic block, we have the value of this. So rho L by A. Now, as this is cubic, so the value of A is nothing but L into L. So a side, right? So this is the value of rho by L. Now we have the value of L here. Where was it? There was the value of L, right? So this is the value of L. So we can maybe write it down as well. So the value of L was 10 micrometers as well. So if we are converting micrometers to, let's say, centimeters, so that would be minus 3 centimeter, because every other thing is in cc, that is centimeter cube. So that's why I am converting it. So we can write it down here. So the value would be rho by 10 to the power minus of 3, right? Or we can write it down later. So what we can do from this is that we can get rho value. Sorry. Yes. So we can directly get the rho value. What is the rho value? And we just need to, as we have already have the value of L, so we have to calculate the value of rho. Maybe we'll write it on the next page. So let's write it here. So the value of rho is how much? That is Q multiplied by N mu N plus P mu P. Just calculate it and tell me the value of this. And also, there's another thing as well. So for this case, as it is already doped, this would be the value, because the value of n is much greater than p. As you can see, the value of n was 10 to the power 16, whereas the value of p was 10 to the power 4. So it is completely negligible. So we can write it as like this: 1 by q n mu n. So there would be some changes after, I guess, 1 2 3 4 5 6. After 6 digits there would be some changes, so that's why we can omit that completely. So based on this, we have to calculate the value of rho, and from that we also have the value of L, which was nothing but how much, which was, I guess, 10 to the power 3, 10 to the minus 3 centimeter. Now we can just put the values there: dVin by di of in, that is rho by L. Let me put the values maybe. So if there is any miscalculation, please let me know again. So just a second. So this would be 1 by 1.6 divided by 10 to the power minus 19. That is the value of Q, divided by N is 10 to the power of 16. So that is 625, and divided by mu n was given as 10 to the power 3. So 10 to the power 3. So this is 0.625. Okay, and 0.625, and this term would be 0.625 divided by 10 to the power minus 3. But this is nothing but 625. Um, the unit of this, let me write it down maybe. So this is 1 by coulomb multiplied by 1 by centimeter square by volt second multiplied by 1 by n is 1, sorry, 1 by centimeter cube. This is centimeter, right? So this would be 1 by coulomb into 1 by centimeter square per volt second multiplied by 1 by centimeter cube into 1 by centimeter. So centimeter cube, centimeter square gets cancelled out. And so this is nothing but C. C is 1 coulomb is ampere per second, right? So this is nothing but ampere second. This is volt second. Second cancel out. So the value of this would be in ohms, and we can write it down as 0.625 kilo ohms. So the value of del VIN, that is the dynamic resistance, del IIN is 0.625 kilo ohms. Is it okay with everyone? Or you have any queries? So this red portions are for unit calculations. So you can omit that. So what we have done here is that based on the doping, we have calculated the carrier concentration, that is for the holes and the electrons, and based on that we have calculated the value of dynamic resistance, that is rho L by A, as this is a cubic one, so A is nothing but L multiplied by L, so that's why it would have been rho by L, and based on that we have put the value, that is 0.625 kilo ohms. So there's still a question remaining. What I'll do is that I'll then, because the time is also at the end, so I'll just give the question, try to solve this, and maybe we'll discuss it on the next class. If like most of you can get this, then we'll not discuss it. But if there are only a few who have done this, so we'll discuss it on the next class. So I'll just write it down. A semiconductor is in thermal equilibrium. Assuming the donor concentration varies as ndx as n naught exponential minus 10x over 0 less than x less than this, and n naught is constant. Find the value of electric field at temperature values of 300 kelvins. So try to solve this on the next session. So we may discuss it on the next one as well. Okay. So thank you for attending today's session. Thank you for attending today's session, and we'll conclude the session here. And we'll have the next session on Sunday from 7 to 9 again. Thank you.